Okay, testing my mic volumes. Hopefully it sounds good. I'll look at the mic, I'll look at the camera, and I'm just going to open up my things here so that we can see you. I'm launching a Zoom meeting now. For all you guys on Zoom, that would be great if you just join us on Zoom. And here I am on Zoom meeting. Okay, welcome. There's participants. We're not quite in the meeting yet. Hopefully we find people to join. Oh, welcome all, guys. I'm just gonna join here right away. Aaliyah, can you try and join the meeting? No, you're not in the waiting room yet. Try again. Okay, try again, because I want to make you host as soon as I can. There's 6 people waiting. Jesse's in. Yeah, I'll send it again here. Jesse's in, so I'll try and send it right now. Good morning, everybody. I see a whole bunch of you here online here. We are going to start our training in just a minute or two, and I'm just expecting another couple to join right away, and as soon as that happens we will get on to the training. So I see we got Alan, we got one person joining just on the phone, which I see there, and right now I've got, I think all of your mics are muted except Jesse's muted, which is fine, you can talk. And in about another minute or so I'm just going to start talking. But good to see you guys all. This is the first training that we've done like this, so it's going to be a bit of a learning probably for both of us. I don't know if you guys have all been online or not yet doing this, but it's a definitely a different way to do it. I'm glad you could all join us in this. I'm going to sort of be a little bit annoyed. I'm hearing you can't hear me. Give me a thumbs up, or Lance. You hear me? Okay, good. Good. I'm going to make Aaliyah as well a message. What do you call it? So Aaliyah, if you can just keep track of participants, if we need to add somebody in, you'll see them on the side of your screen. If you could add those, that would be great. And I'm just going to do this, so if you can add people as they join, that would be great. So I see we've got a couple people here, Alan Weens, Jesse, Aaliyah, Nolan, and the one on the phone as well. I'm just going to unmute you guys one at a time. Actually, I'll unmute you all for a minute and we'll say hi. Maybe I can unmute everybody. Oh, I can't. I don't know how to do that. Aaliyah's got to unmute. I guess if I can't unmute you, I can't really say hi. Good morning. Was that Lance?
It is, yeah, you bet.
Good to see you, Lance. Thanks for joining us.
Thank you.
Harvest. I see we got a harvest here. Which which, can you unmute Harvest, Aaliyah?
I don't think they have
Okay, they might have done a phone in. So anyhow, we'll start. I'm not sure how to say hi to everybody. Aaliyah might get that. I'm going to go through on this. I'm going to put a screen on here as well. So you'll see the screen, the PowerPoint as I go through. It should take about 45 minutes or so total. So it won't be real long. And we're going to have some good, hopefully some good learning on here. So I'll start a screen. I just have to figure out how to start my screen. I'm sure there's a better way to do this in between, but I haven't mastered this totally yet. So I'm thinking that on the screen you guys should be seeing here in pretty quick a background that'll say measurement errors found and fixed. Does that come up? Okay, so we're going to talk about some measurement errors, some things that we found. There's a quote here I like from Pablo Picasso. He says, learn the rules like a pro so you can break them like an artist. So we're going to learn a couple of things here, hopefully. Learn a few rules, a few things that we can take away from this. A few of our takeaways. So for a virtual training, actually everybody seems to have names that make sense. Alan, Nolan, the phone. I don't know how to rename the phone. In fact, can I unmute these guys? No, I do not know how to do that. Sorry, I'm not a whiz at this. So welcome to this virtual training. And if you could rename your screen, if you can, just put your name and your company. That's a little option on the side there you can do, and then we'll know who it is that we're talking to. But in the meantime, we will just get on to this. Daring ideas, this is another quote. Daring ideas like chessmen moved forward. They might be beaten, but they might start a winning game. And so we're going to discuss some ideas today. Some of my ideas you might want to beat down at the end of the day, but it should start a discussion on what we can discuss, what we can do, and how's some better ways to do it. Okay, some discussion items that we're going to talk about today. I got about 5 or 6 things on the list, and I'll just talk about it, and then I'll see if I get a thumbs up or a thumbs down on any of these ones. But we've got water cut analyzer was accurate at 12 degrees Celsius, but went way out at about 11 degrees Celsius. There's a Coriolis meter that passed verification, but was incorrect in density and volume. We're going to talk about fresh water meters with our fresh water in emulsion and how that caused incorrect water cut. We'll talk about a couple of identical meters on the same water line, both ends of the same water line, and about 7% difference between the two, and what we found, how we fixed that. As well, a couple things, Coriolis line balance meter with some change, and some new super skids that have, there are new wells, brand new meters, and there's density errors on them, consistent in the same error. And then we're going to talk about dump valve passings finally. So those are some of the items that we're going to discuss in here. So if I showed you a little sheet there, the phase dynamics, we're going to talk about some different types of Coriolis that we've ran into troubles with. We're going to talk about the some turbine meter issues, different ones, different totalizer issues, some different micromotions, and then we'll end up with dump valves. Dump valves is one thing that you might not have these other meters, you might not have the same brands. Every one of you has got dump valves. You might not have the same D2, but you'll have a dump valve on every test separator you've got, and that's a big cause of issues that we find. So those are the things we're going to go through. We'll start off, there's this phase dynamic water cut analyzer. We verified it just fine in the fall, and we verified it like summer and fall. It seems to work just good. It was a quarterly verification, so it got done a couple times just fine. And then in the winter, we noticed there was a huge error in it. And so the way we kind of calibrate these is we do a sample. We see what the analyzer is reading, and on our little sheet here, this analyzer, the first one read 64%, and we pull a sample at the same time, and we find it was only about 55%. So there's about 8% difference. And we did this several times here, and we found that the variance between what our sample was and what the meter read was somewhere between 8 to 16% difference. And the analyzer was reading quite high all the time. So we found that there's that error, and we attempted to do a calibration on these. I sometimes discuss exactly the calibration. I won't go over it. We tried to calibrate it, and we did the calibration properly according to the manual. We find the salinity range internally goes to 8%, and the calculations were still over ranged. So what we did is we went through the programming on it. On the screen you can see it'll show water cut and oil and water density and a salinity. And on this type of screen, this is something on the phase dynamics, but it's on lots of different ones. You'll see it's got a range. 8% is the high, 0.1% is the low, and it was at 8%. And that is actually, that ended up being the key to what was the issue. It was 8%, that was the full range. It was at the very end of the range. So to fix that, the factory engineers modeled it. They found the problem. They found that this was a temperature issue because the density varies with temperature. 11 degrees Celsius and below, it wouldn't work. 11.1 degrees and above, it was right exactly where it should be, and it's currently at 4 degrees Celsius. Some of these instruments, you talk to the guys and they live in some warm climate, and this guy lived in, it's trying to think where he's from, in California anyhow. They're in California. They're like, why are we only at 4 degrees Celsius on our tanks? It's like, well, we live in Alberta and it's winter and it's cold. And 4 degrees is not uncommon for shipping tanks, and or colder. But it might affect others as well. We actually found a resolution. The phase dynamics were able to make a new configuration file, and once we put in the new file, they made from 0.2 to 11%, and the actual was 10%. Really what the issue was is it was trying to enter a 10% thing into a table that only went to 8%, and that's why it got the internal error and made all the issues when the density changed. So that's the first one that we found. After we did the same test where we see what the analyzer reads, pull a sample, and we did 3 tests, it looks like, on this one, and they're all within 0.2 or 0.3%. They're all within the 0.5% tolerance that this meter has. So as left, once we changed that, it was fixed. So just our point, what could we learn here? Watch out for settings that are at the very end of their range, because that's, if they're at the end of the range, maybe they're actually out of range. This one was really a 10.2, and internally it was trying to set that 10.2 on a table that went to 8, and it caused grief. So I'm going to tell you a joke. Hopefully that you guys can laugh. If I can see your thumbs up if you're laughing too. Okay, I wrote a joke about COVID, and I told it a few days ago, and nobody got it, but eventually everybody did. Okay, so that's my good joke for the day. Next, we'll talk about 2 different Coriolis meters, and if I can make this work. Okay, there's 2 different Coriolis meters. Both passed verification and both had reproducibility and density errors. The first one's on a sales meter. It's a 2-inch Coriolis pumped oil. There's a lot of difference between runs. We did a regular proof. It was a regularly scheduled proof. And the meter factors from 0.95 to 1.01. There's 7% variance between runs. Typically, Coriolis sales meters that are pumped are well within a 0.5% difference between runs. We found the densities were off, the flow rate was reading incorrectly. We checked all the programming and it was correct, and the meter verification passed just fine. And so we're like, well, what could be wrong? We did a prove, and it's a 2-inch Coriolis, and here's sort of the proving numbers after your temperature correction. We put 900 liters in, and the meter recorded 965, and the factors are on the bottom: 0.95, 0.96, 991, 1.02. They're sort of all over the change, and the repeatability is this bottom number in the yellow called run repeatability. There's, on 4 runs, there's 7% between the max and the minimum, and this needs to be 0.5% on a sales meter. So we got them to schedule a cleaning of the meter, thought perhaps there's something like that, something to be lodged in it. And really what we found in this meter is, although it passed verification multiple times, it was clean, it was free of debris, something internally had come apart in the meter, and the manufacturer needed to repair it. Once it was repaired, it was good, but it needed to manufacture repair, although there was nothing observant outside at all. It looked good, it passed verification, but it would not pass a physical proof. So the second meter that had similar, it passed a verification. Here's a picture of it. It's a Coriolis, the triangular shape, a 1-inch Coriolis meter. It's as well on a line that's got a pumped emulsion through it. And the problem that we heard reported was the water cut is way out. It's a sales custody transfer from one company to another with pumped emulsion between it. And the water was way out. So we thought there's a few issues. We thought maybe the sensor tube or core processor, transmitter, the flow boss, or the rock knock. Really, it could be any of those issues. And so we did some initial troubleshooting, and we thought, what is this trouble going to be? And we connect, and there's lots of errors that it showed, lots of different errors, which aren't uncommon when you see some issues. To see some of these errors, they can stay in there for a long time. But there was lots of errors. Transmitter warming up just happens from a power failure. Transmitter failure you don't usually see, but occasionally you see that when there's a restart or a power cycle. Sensor communication failure. Some of these could just be normal from a poor power or something. But anyhow, there was lots of codes in this one. We data logged it for a while to see what was actually going through the meter and to see how our things were really working. And we found that the density, the Coriolis showed a density of about 0.96, 0.97. The temperature was 5, which was actually right. The drive gain was around 47. The flow rate 127. The flow boss density agreed exactly with what we saw in the transmitter itself. But the actual measured density was about 1.05 to 1.06 with water, and the real water cuts weren't 40%, they were really about 90%. We did a whole lot of troubleshooting at this. We saw lots of these error codes, and they really made us question what the, if there was something wrong. And so we did some, I'm not sure if these guys say don't talk too technical. I won't talk too technical, but we disconnected the core processor and transmitter. We powered it with a portable power supply, which is a good way to know if you have a transmitter issue, anything with a power supply. This meter then was totally powered separate. We still had the same density errors. So that pretty much eliminated everything but the core processor to being a problem. Again, we performed a meter verification, and it passed the same densities. Same error on densities that we had previously. So we did some more troubleshooting and consulted with manufacturer or anything else. The manufacturer suggested there might be a soft wax coating, but we removed the meter. We did what we thought was a good way. We put a wire and pulled a really thick rag through each of the tubes. They were clean, there was no wax, there was no debris, and both sides were clean. We did a very temporary fix so that we could see if we could make it work even approximately. So we did we fudged the numbers by changing the internal numbers, so we got it approximately close for a reading. Even with the temporary fix though, although we got the numbers to read about right, there was a large variance between runs, still about 5% variance between runs. Meter verification passed 2 more verifications though, and it worked well. So we ended up having to pull this meter out to the shop, And we put the meters, the factories back, everything back to factory settings, and it showed exactly the same in the shop as it did in the field. The density was showing like 0.91, where really we were 0.99, almost 1. Our drive gain was still really high. It had the same problems. What we did next, we put a boroscope through. This is like a triangular shaped meter, and we stuck a boroscope down internally into this meter. And what we found is 12 inches was clear, which would have been to almost this far, like almost down, halfway down the tubes. And then there was a black coating that started, it just looked like a black plastic coating. With the boroscope, it was pretty obvious. It just looked like the tube was coated just beautifully. It's a thin black plastic coating. We cleaned it out. We weren't really sure how to do that, if we should use chemical or what. We weren't sure what the coating was from, but we tried by heating. These meters are good for about 200 Celsius, so we thought we'll just heat it up slowly. And around 50 Celsius, the coating heated and softened, and around 65 Celsius, it turned to liquid, and we turned the meter upside down and dumped it out. So it was actually, once it was hot, it dumped right out whatever the melted plasticky stuff was. And then it hardened again. We dumped it, and we kept that, of course, and it just looks like hard black plastic when it was dumped out. After it was clean, we inspected again. We did a shot prove, and once we did the shot prove, the density lined up nearly exactly what it should be, and the drive gain 4.8%. The numbers, the repeatability between runs is 0.02%, almost exact repeatability. Remember when we started it was like 7 or 8% between runs. It passed verification, but in this we learned, don't put 100% of your faith in the electronic verifications, but especially if there's any indication of a problem. We just can't trust those verifications all the time. I've been told by the manufacturer that these verifications will sometimes, the newer version should work, although we were using 2018 version of the, this is a meter made in 2018, so it's not really old. The newer ones made in 2019 may have picked that up. But anyhow, there's not a lot with meters, like a lot of the stuff we see is older than 2018 for sure, so they don't always work even though they should on the electronics. We learned something else at this same site. So I put it into the thing here. It's inferred water cut. Lots of times when you use a Coriolis type meter, they use the density off of that to figure out what your water cut is. If you know what your water density is and you know your oil density, you can determine the water cut. And it's very common if you have these meters. It works well with it doesn't work so well from, like, say 90% up or 0 to 10%, but if you're from 10% to 90% water, it actually works quite decent most of the time. But when we were out there, we measured the oil and water density, and we found there was a big change in their water density. Normally it's really heavy water in this area, 1.15, and it had changed to 1.09, which is still fairly heavy, but operation says there's a source water now coming into the line, so being how we have a lot of fresh water, it's changed our water density. And so we entered the new density thinking that that's what it is when we were there, and we really shouldn't have. We kind of asked ourselves after, what did we do wrong? What was the effect? And what happens if fresh water was shut off? Well, when they told us this was right and we entered the new density, we measured, it would have been perfect the day that we were there. But any time that the fresh water amount changes, then their water density changes. And if the fresh water is cut off, then it's going to be a lot heavier than that, and it's going to show a lot higher water cut. If there's more fresh water, it's going to show up as more oil. And you really can't have three products in the mix. With that fresh water changing the density so much, it really affects the thing. So really we can't use that density to determine water cut if your densities change. There can't be three products in the mix. Here it was fresh water, salt water mixed together into a water, but really the fresh and salt, if the ratios changed, it made a huge difference in their oil percent water cut. Okay, this is another one on an inlet separator. Oh, there's a 1-inch meter. It seemed good. It seemed like it's a new setup, but there's 6% variance between the runs on this new setup here. And it had one of these meters. We found that the condensate level controller was set for throttling action, which you guys have a lot of different level controllers. L2s are really common, and so are some other brands, but the North Seal and others. But they can be switched between throttle and snap acting to control the dump valve. And what we found on this, when the meter would go slower than about 20 cubes a day, the meter factor would drop way below 1, and it showed very inconsistent repeatability. When it stayed above 20 meters per day flow rate, it was accurate, it was repeatable. As found, this is just the as found runs. Again, the bottom number, we can see there's about 6% between the 4 runs, repeatability. And then we had one of those duh moments, you know, and every meter around has flow rates. If your Coriolis, if you're a turbine meter, there's an accurate range where they work. And you know, some have different, you know, these are both 1-inch meters, both made by the same manufacturer, but the flow rates are, say, 10 to 195, 6 to 650. The flow rates can be quite different on the different meters, and they sometimes work better at the low, like some meters work a lot better at the low flow rates than others, or the high flow rates. If you have a turbine meter, which is really common as well, they work about half the recommended flow rate, they quit counting. These Coriolis read high when they go, when the flow rate gets too low in this application. But what we found is the controller was the throttling control. We just changed it to snap acting. On this, it took a different relay change. We were able to make it snap acting, and then the flow rate dumped at the same flow rate each time. It was in the accurate range of the meter, and it was consistent. Instead of throttling up, down, 18, 20, 19, 25 kind of thing, it would dump consistently at about 60 cubes a day, and just consistent. Every one was at 60 cubes a day. And again, when we were done that, we did 4 runs after changing it, 0.04% repeatability. So by changing that to where it had a throttling valve, different flow rate every dump or throughout the dump, to a constant flow rate, it went from somewhere around 6% between runs to 0.4% between the runs. And we learned that snap acting control valves, they need that to keep it consistent. The meter needs to be in the recommended range as well. The snap acting control valve is actually right in the directive, the Directive 17 in Alberta here, that your meter must be upstream of a snap acting control valve for measurement. And so it's actually right in the directive. It's one thing that sometimes works either way, but really it's if for whatever reason your meter or your control valve is throttling and the meter goes below the range, you just don't get accurate readings on it. Okay, next is 2 identical meters. We have these 2 water meters. They're fresh water meters, a source well, it's on a source well. The line is a little less than a mile long, the same meter on both ends, the same totalizer on both ends, identical meters, and identical, everything's identical both ends, and it's the same line. They're turbine meters, which you see a lot of them on different applications, but certainly you see turbine meters on water and condensate and things like that. And being that there's 2, we had a good comparison all the time. They should be exactly the same. It's the same water going through both. They were identical meters. The recommended rate on these was 3/4 inch, so 11 to 80 cubes per day. They were running at the lower end of their range, mostly 18 cubes a day, but sometimes they drop down to about 10 cubic meters per day, but they never could find it ever going below the 10 cubes a day rate. It was, you know, it's pumping and it's throttling, but being that it was fresh water, they never wanted it to stop because it would, you know, because of freezing issue, they wanted it always flowing. But it would flow sometimes, like mostly it was 18 cubes a day, but sometimes it would dip down to 10, which is still right in the recommended meter factor. They're water meters, so they pull them out to bench prove them, and that's very normal. But because these were also water meters and pulled out, they're on a SCADA system, so the totalizers were connected to SCADA, and they were never brought into the meter shops when they were doing the calibration. They looked though like they should read the same. We thought, what are some of the possibilities there? And some of our possibilities were the totalizers could be programmed incorrectly. They might be under range, not turning, a damaged probe. So we proved these meters. We got the same number. We were actually the second shop because we were called in to do the troubleshooting, and we got the same numbers that the previous shop had got. There's no issue that we could find with the meters, with the meter factor, or with the previous prove. And yet the meters did not line up at all. The meter internals, we switched meter to meter, and although the numbers are slightly different meter to meter, with the same turbine on the same impeller inside, give a same pulse count no matter which meter it was in. Switching the probes didn't seem to make any difference. Everything seemed to be consistent. The totalizers, again, I'll bring up, they were hardwired in, so we didn't see the totalizers. He explained which ones they were, and they were one that they weren't as popular as some of the other. I wasn't really familiar with them. I got out the book to see what they found, or what the totalizers said in them. But because they're water meters, the totalizers never come to the meter shop with them, especially when they're hardwired in. So we verified the pulse voltage from the meters, and then we noticed something. Normal flow rate, these have the pulse output voltage, you measure it in millivolts, just they're an AC millivolt signal off of that pulse, and it goes from 11 millivolts to 1 at 18 cubes a day. The one reads 11 millivolts, the other reads 17 millivolts. And we tested when they would count. We found both meters in our shop counted really good, right down to 9 cubic meters per day, which was slightly below what they ever did. But then we dug out the totalizer specifications. Remember, we don't see the totalizers with these ever. We found they had a trigger voltage of 10 millivolts. And really what we found is these two meters, although they were identical in just about every respect, the one had a lower voltage output, and so most of the time if you were at 18 they would both count the same. The other one would drop, when it dropped to about 16 cubic meters per day, the millivolt would drop below that 10 millivolt trigger level and would quit counting. And the one that they kept looking at the flow rate would happen to be the one that counted all the time. It was the one that had a higher voltage on. And so anyhow, finding that millivoltage output, we end up, it's like, hey, there's a problem. We found a simple solution here to this one. They're 3/4 inch turbines, and on turbine meters, the internals are sometimes different internal size in the same meter body, but a 3/4 inch turbine really has a 1/2 inch meter bore in it. And so we were able to just put a new kit, a 1/2 inch kit, and converted the 3/4 to 1/2 inch with a simple repair kit. And when we did that, we did a bunch of tests. We find the 1/2 inch, it makes a lot more voltage output at 17 cubes a day, 26 to 28. And the low flow, they both counted down to 4 cubes a day. But because we didn't have that one in the shop, the other thing we really learned out, the shop doesn't get the whole story when you do a shop proof. The totalizers never came to the shop. They're water meters, so they don't need to come to the shop. And they usually, they don't have to come to the shop. In this case, they did. Or they didn't. But if they would have, we would have been able to do a test with the actual meter and slow the flow rate down. I would have noticed right away that, hey, this one quits counting and this doesn't. With our shop totalizers, and with several different brands of them, they'll count to 3 or 4 or 6 millivolts. The 10 millivolt cutoff is higher than some other brands, some popular brands. And with the shop one, because we're always dealing with different ones, we set our shop totalizers to a high sensitivity typically. And so in the shop, these meters work good. If we would have had the whole meter system with us, it would have been good. Or if we would have done it in the field, which here they didn't have any good way to do that. But if the meters need to be in the recommended, but sometimes the shop really doesn't get the whole story. Especially this, it worked good. If we would have had a shop, one of our shop totalizers or a different branded totalizer on them, they wouldn't have had any issue at all. Okay, Coriolis line balance meter. This is one that we had another trouble with, it seems like we've been having lots of Coriolis meter troubles in the last while. So anyhow, that's one. It's an NGL sales line just for balance. And this meter was put in 3 years prior. And the first year it was put in new, it wasn't proved. It didn't need to be proved because it's just line balance. And a meter factor of 1 was used. It had a density of 505 for the density. Year 2, they brought in a ball prover, a bidirectional ball prover. It's very accurate. It's probably the most accurate proving way you can do. They used a meter pulse count of 500,000 pulses per cubic meters, and it gave them a number. They should have maybe figured out that why would they put 500,000? That most are set at 100,000. Occasionally you'll see one set at 10,000 or something, but the majority are set at 100,000 pulses per cubic meter for the ball provers to use. But it worked. It was a 3% shift, and there's no density on the ball prover, so the density wasn't verified. In year 3, the same prover, the same settings, they shifted another 3% to a new meter factor of 1.06. And of course, now that 6% difference from what the other land is showing with once they enter this new meter factor, and so it's always showing that there's a leak in the line. This is sort of hard to see on this meter. I should have done a zoomed in meter. The flow comes down the pipe on the left through a strainer, and then the meter is sort of behind all the goodies. That's the real meter. We connected with a portable meter in the middle of the plant. It's hard to get to, but we carried a meter in on one of our portables right to the plant to connect to be able to do this job. And we proved the meter, and we proved it 3 different ways. We proved frequency to volume. That's the way that it was previously done, so we could do a good comparison to the ball prover. Then we can prove volume to volume, and we also proved it mass to mass. When we're doing troubleshooting, we sometimes like to do the different proofs. We have the we have the ability to prove it the 3 different ways, so we did prove all different 3 ways on this one. What we found is proving volume to frequency. We got basically the same number. That's the way it was done previously with the ball prover. We got that same meter factor 1.06, same as the ball prover got. We found the density was quite different, 480 grams per liter than when it was originally put in. But we got the same factor as the ball prover did. And so we're thinking, well, that's what they got. But then when we proved this thing volume to volume or mass to mass, we got a totally different number, a 1.008 type of number. So very different than the volume to frequency number. And you know how when sometimes you go to the airport and they ask you, did anybody put anything in your luggage without your knowledge? Well, sometimes when you're doing meter proofs, you find there's a lot of different ways you can program things, and lots of different programmers program them different. And at this, we found that the frequency output that got used for the proving, which is normally set 100,000 pulses per kilogram, or 100,000 pulses per cubic meter, was set at 1,000 pulses per kilogram. And they also put in a fixed density in this one of 506, which is what they had the day that they put the meter in 3 years prior. But our observed density had shifted over time to 480 grams per liter. So there's a shift in density, which is exactly the amount that between the shift in density, that's the exact same ratio of the amount of the 1.06 that we found. Sometimes we call this an ID10T programmer. If you have that written out, you'll make the change in base in meter factor can be explained by, they used an assumed base K factor of 500,000 and the real base K factor of 1,000, and they also used the assumed density. But because there's a shift in density over time, it changed the output. Once we figured out the new factor and thought this volume to volume is this, and we put in the real factor, then they came up, everything was in balance, and they were all happy after it was all fixed. Just a couple more things that we looked at that are, there's one more about a Coriolis, and we'll talk about the dump valves. There's these new super skids that are coming out, and on some of the new wells, they have a couple different sizes of skids. In the high production wells, they use a 2-inch meter, 2-inch everything, and the little bit lower production, they use 1-inch meter in. And we found the ones with the high pressure wells, the densities were reading low consistently, every one. And it makes the volume read high, and the meter factor then has a number that's less than 1 by that same amount. And so we got digging into this a little bit, and we found that on certain meters, a 2-inch, there's a process effect on density. This is actually right in the book when we read it, but it's something that we've never seen with any other brand or any other model of these meters, even the same brand. So we didn't realize that there's a process effect on the one size of meter. It doesn't sound like much because it's a 0.0003 grams per cubic meter, but in reality, these meters are on new wells running 7,000 kPa, and it's 3% error. It causes a 3% error on these certain ones. It makes meters always read low by 3%, and then the meter factor is around 0.97. And we had a smart guy pick this out. It's like, hey, how come all your things are reading like there's a trending the same way? What are you doing wrong? And it's like, yeah, we want to know what we're doing wrong too. We never see a trend the same way. But if you do a bunch of meters in the same area and they're all trending, like these ones were all reading low, and then as soon as we figured out, hey, the 2-inch ones read low and the 1-inch ones don't. Actually, the other way around. But when they were all trending the same direction, we had to dig, and this one, it was right in the manual. When we dug up the new manuals, it says there, that explained very much. But sometimes you have to, when there is something and you see this, dig out, see why. And like I said, in this case, it was right in the manual. It explained the error. It was the exact error that we saw. It was right explained there really well. Okay, now this is the last one I'm going to talk about for this morning, and then we'll see if there's a question, if I can figure out how to unmute everybody. But I put this one in at the last because it's the most frequent measurement issue we find in the field. When we studied our percentages a while ago, we went through all the different things we found wrong, and this was probably twice as often as any other measurement issues, is your little dump valve. On every test separator in the field, every inlet separator has a dump valve controlling the level. And it affects virtually on your oils, your waters, your gas. Every meter, remember we've talked about there's a minimum flow rate and a maximum flow rate on every meter. And lots of these in the field, you'll have a turbine meter. And on the turbine meter, or if you're from the States listening, a turbine meter, they have a flow rate. If you're a 1-inch turbine meter, they have a recommended rate, 27 cubes up to about 270 cubes is a pretty standard one. And if you have the 1-inch meter, it doesn't start counting till about 10 cubic meters per day. So if anything's dumping below that range, it's the instantaneous flow rate you're worried about with the meters. It's not my well only makes 2 cubes a day. It's the instantaneous flow rate when it's actually dumping needs to be in the meter range. But if your valve is passing below that range, you don't notice it, especially if it's a little. You notice if your dump valve is passing a whole bunch and it's going, like your separator's got no level in it, you'll notice that. But if you're making on a well, like say a low production well, it's making a cube a day of condensate, and your dump valve is passing like 0.2 or 0.3 of a cube a day, you'll never notice that from operations point of view. They get missed so easy. It looks as though the production's dropped slowly over time, and it's very often assumed that's what the issue is, but it can easily be a dump valve passing. So I just want to talk about that, and I guess you have to check the dump valves. Ensure they're holding 100%. There's several ways you can check them. But if you're a meter on your line with a 1-inch turbine, it can pass 10 cubes a day. If you're some of the bigger ones, we often see the new ones will have an 1.5 inch turbine, and you can put 20 cubes a day before you start turning the meter or so. And even if you have a really tiny meter, say a 1/2 inch meter, they start turning about 2 cubes a day. So you can still put a cube a day through a passing dump valve, and it's really easy to not notice your passing dump valve if it's leaking less than what your production is. I say it can be passing a cube a day on a 2 cube a day well, and you might never notice. You might think, oh, this production has dropped off. That's all it's making. So when you see the dump valves, verify it 100%. In summary, with the dump valves as well, I'm just going to back up for one. As I think, lots of people just look at the meter to see if the meter's turning when the dump valve is passing. But again, there's a minimum, even on, it doesn't matter if you use a Coriolis meter or what the technology is, there's that minimum flow rate. A 2-inch Coriolis typically has got a low flow cutoff set at 7 or 8, maybe even 10 cubes a day. So even on a Coriolis, it doesn't really matter the meter technology. That's still, if it's under the meter range, you can't look, say my meter's reading 0, my dump valve's holding. Okay, so summary. There's settings at the very end of the range. If you're looking at something and the settings at the very end of the range, question it. Maybe it's a little bit over that setting and it's out of the range and you don't notice. Second thing, density. If you're using density to determine your water cut, you really can't have 3 products in the mix, whether it's fresh water and salt water and oil, or whether it's condensate or oils of different varying densities with the same water. You can't have 3 different mixtures of product if you're dealing with using the density to determine the water cut. Use snapback to control valves. If you got a level control to keep your flow rate consistent, the dumping flow rate consistent while it's dumping, a snapback to control valve, and plus that's in the directive just to be compliant. Your meter, it should dump at the recommended flow rate. Lots of them are very low. On a turbine meter, it's not uncommon to see a 1-inch turbine meter. They count pretty accurate right at the bottom end of the range. But make sure you know what that meter range is and dump in the rate. We have some cheat sheets with the meter, a lot of different meters recommended rate sheets. If you go on our website, mes.ca, meas.ca, you can find some of the meter dump rates for the recommended flow rates for some common meters we see. And then finally, shop proofs. They don't get the whole story if you take a meter to the shop, especially if it doesn't come with a meter and the totalizer and the whole system. The one that we found in our example, it came to us, it came to another. The meter proved good with our shop equipment. It proved perfect. If we would have been on site or we would have had the totalizer, we probably would have found that error a lot quicker. And then a couple more things. Look for programming that's different than expected. Especially on these Coriolis meters, some new technology. Coriolis meters has factors entered in at least 3 places, sometimes 4 places, but it can be entered in the transmitter, in the rock, in the HMI, and several different places in the HMI, and they all need to be correct. So check your programming, but especially if you're having issues, check all the different spots that these meter factors are, and check it right through from the meter to the end screen that you're getting your number off should be consistent across the board. And then passing dump valves are our final thing. They do cause the most measurement issues that we find in the field in our experience, so verify your dump valves hold 100% all of the time. So Aaliyah, if you could just unmute everybody, and if anyone has questions, I'm open for questions.
If they can't do the mic, they can also use the chat.
Okay, yes, you could also send a chat. So any questions? No questions? I'm going to point you guys to our, if you want a meter flow rate sheet, you can get a PDF of that right at our website.
Pretty straightforward, Gary.
Pardon? I missed that?
I think that was Alan.
Oh, I think I missed you, Alan.
No, it wasn't me.
No?
Oh,
This was good, Jerry. Thank you very much.
Well, thank you guys for joining. It was good to have you. Hopefully we could learn a few things, and hopefully you all learned at least 1 or 2 things. And thanks so much. But if you got any questions, feel free to send me an email. My email's on the screen, or it's jerry@measurementengineering.com. I see I got a typo in my email on this screen, but there should be a .com. Or the website is mes.ca is the shortest way, meas.ca. If you want to type out measurementinc.ca, that'll also get to the same site. And my email is there. You can certainly give us contact through any of that. So thanks so much to everybody for joining, and good having you. And if there's no more questions, we will let you guys get back to your beautiful work days.
Thank you very much.
Thank you very much, Gary. Thank you, Gary.
Thanks then.
All right.
Okay. Bye.
I think you want to end it.
Yeah, I don't know how. You have to end it. You're the